Should be a few more people coming in, but that's all right. So I'm going to start chapter 12 today. And section 1 deals with types of mixtures. Now, the first part of this should be some basic review of mixtures and solutions. Some materials, it is easy to see that it's a mixture because you can see the component parts, but others like milk do not look like mixtures, but they are. You can see round droplets when you put it under the microscope. So that makes it a heterogeneous mixture. If you remember the difference between heterogeneous and homogeneous mixture, heterogeneous is where it is not a uniform composition throughout the mixture. So if you take samples from different parts of the mixture, you're going to have different component parts. And the opposite to that is a homogeneous mixture, also called a solution. So for a heterogeneous mixture, the composition is not equal. On the other hand, if you take sodium chloride and water, they form a solution or a homogeneous mixture. So if you take samples from different parts of the mixture, you will get the same proportion of the component parts. Sugar is another example. Sugar is soluble in water. The word soluble means it has the ability to be dissolved. So the question is, what actually happens to the sugar as it dissolves in the water? If you have a lump of sugar or even just crystals of sugar, it starts to disappear as the sugar molecules leave the surface of the crystals and mix with the water molecules. So dissolution, which is the process of dissolving, dissolution, happens at the surface of a solid. So if you have a cube of sugar, then dissolving is going to take place at the surface because that is what's touching the liquid. Eventually, all of the sugar molecules are going to be evenly spread through the water molecules, and all visible traces of the sugar are gone. At that point, it becomes a solution, which is a homogeneous mixture of two or more substances in a single phase. Now, there's two parts to a solution. You have one substance which is randomly mixed with particles of another substance. The solvent is the dissolving medium. In a solution, most often it's going to be water. So dissolving medium, and the solute is the substance that is dissolved in a solution. So in the previous example of sugar and water, the solvent is water and the solute is sugar. The solute in a solution is usually less in quantity than the solvent. The dissolved solute particles also cannot be seen. They're going to stay mixed with the solvent forever as long as conditions stay the same. If you start to change the conditions like volume, temperature, things like that, you start changing the conditions and you're going to change the solubility, which is something that we'll talk about a bit later. Now, solute particles range from between 0.01 to 1 nanometer in diameter. And the reason why I distinguish between those two, sorry, I keep going in and out of full screen, but I'm letting people in. The reason why we distinguish between the sizes is because a little bit later on, I'm going to talk about suspensions and colloids, and the difference between a solution, a colloid, and a suspension is particle size. So this is why I mentioned particle size now. Solute particles for a solution are between 0.01 and 1 nanometer in diameter. Now, solutions can exist as liquids, gases, or solids, any mixture of those two things. So here's just a table to give you different examples of solutions that are in other phases besides having the solute as a solid and the solvent as a liquid, which is usually the most typical example that we use, either salt in water or sugar in water. So just examples, we've got if both solute and solute are, if both solute and solvent are gases, an example of that is basically air. So air is made of just rounding 80% nitrogen, 20% oxygen. So that means that oxygen is the solute. It is dissolved in the nitrogen, and both of them are gases. If the solute is a gas and the solvent is a liquid, an example of that is carbon dioxide dissolved in water in your carbonated drinks like Coke, Pepsi, Fanta, things like that. That's where you have carbon dioxide gas dissolved in a sugar water. If you have the solute as a liquid and the solvent is a gas, an example of that is the water that's in the air. Liquid, alcohol in water, any of your alcohols like beer, wine, spirits, those are alcohol that are dissolved in water. If you have a liquid solute dissolved in a solid, this example is mercury in silver and tin, which they don't use anymore, but they used to use in the dentist's office when they filled cavities. They actually used to use liquid mercury dissolved in silver and tin, which is why if you've got like older parents or grandparents and you ask them about their cavity fillings, that they are silver in color because they used to use that. Nowadays, they use, I think, a ceramic mixture, which is more like enamel colored and also doesn't contain poisonous mercury. That's the other thing. If you have solid and liquid, of course, that's sugar and water. And then we have alloys, which are solids dissolved in solids. I'm going to talk about that now. So an alloy is when you have two solid, usually metals, but you can also use carbon as well, that are mixed together when they are in the molten state and then they solidify. So we have brass. I'm sure you've heard of brass before. That's a mixture of zinc and copper. Now, brass is kind of a goldish color, so it can kind of, it gives you the look of gold, I suppose. It's a bit more red than gold is because of the copper, without having to spend an enormous amount of money on gold-plated things. And then you have sterling silver, which is a mixture of silver and copper. Now, the reason why we make sterling silver is because pure silver oxidizes over time. And so that's why if you have anything that's pure silver in your house, it needs to be polished periodically. And so then we make sterling silver so we don't have to polish it, but it still looks silver. You also have what do you call it? Alloys of gold. When you go to a gold shop and you see the different categories of gold, like you've got 18 karat, 24 karat, like that, because pure gold is 24 carats. And pure gold is quite soft. And so it doesn't make a lot of sense to make a lot of jewelry out of pure gold, especially when you talk about like rings and things like on the hands, bracelets that might encounter some impact damage and get scratched. Like you can literally take your fingernail and scratch pure gold. And so what they do is they mix it with silver, because silver is a harder metal. And that's going to take down, of course, the purity of the gold. So you go from 24 to 22, blah, 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 and you go on down to lower, lower quality golds, but it's mixed with silver to make it harder. So when we create alloys, we're basically, I talk about gold on the next slide. When we choose alloys, we're choosing the kinds of metals and the kinds of percentages to get the properties that we want out of something. Bronze is another alloy. Since the, what do you call it? The Olympics just finished, we have gold, silver, and bronze is an alloy. Okay, so here we go. We got pure gold on the left-hand side. I know the text got kind of erased down here, but this is 24 carats as pure gold. But again, it's very soft, so it doesn't make sense to make jewelry out of a metal that is soft. And so we form an alloy with silver to increase the strength and the hardness, but it still looks like gold. So depending on what the percentage of silver that we add, you get anywhere between 24 and 14 karat. And that's just a measurement of how much silver is added. Okay. So from solutions, now we go to suspension. A suspension is if the particles are so large that they can't dissolve and they settle out. They settle out of the mixture unless it's constantly stirred. And a great example of a suspension is sand and water. And remember, I told you that the distinguishing factor between solution, suspension, and colloid is particle size. So particles that are over 1,000 nanometers in diameter are considered suspensions. So here we've got on the right-hand side, this is what you call a colloid, which I'm going to talk about on the next slide. And this is a suspension. So if you first mix it up and you shake it, it might look like the picture on the right-hand side, but if you let it sit over time and the solute settles to the bottom, then you know it's a suspension. So solution, just to review, solution is between 0.01 nanometers to 1 nanometer, and then we've got colloid in the middle, which is coming up next, and suspension, which is greater than 1,000 nanometers, which would be a micrometer, I think. Yeah. All right, and then we have colloids. So colloids are colloids are mixtures where the particle size are between solution and suspension. So that would be anywhere from 1 to 1,000 nanometers. And these are called colloids or colloidal dispersions. Okay, so between 1 and 1,000. So if you think of muddy water, you have large particles of soil that are going to settle, but part of the water is still going to be cloudy because of the colloidal particles that stay dispersed in the water. Even if you filter it, the colloidal particles are small enough to pass through the filter, and so the water stays cloudy. So this is a great example of a colloid where it's just the particles are too large to dissolve, but they are small enough that just purely from the movement of the water molecules, that is enough to keep them suspended evenly throughout the mixture. For suspension particles, they're too large and heavy, so they're going to settle out. The movement of the water molecules isn't enough to keep them suspended in the mixture. Right, so I just said that for the movement of the surrounding molecules, that's enough to keep them dispersed. So the colloidal particles make up the dispersed phase, and water is the dispersing medium. Dispersed, dispersing, it just means to spread. Okay, so the colloidal particles are the phase that's spread out, and the water is what is spreading them out, because the water particles can move around because they're liquid. Now, unfortunately, one of my favorite labs to do is making an emulsion in the form of mayonnaise. And so this is another kind of colloid. What I call mayonnaise is called an emulsion. A foam is also a colloid, but mayonnaise is an emulsion of oil droplets in water. So what is an emulsion? Okay, what do we know about oil and water? We know that oil is nonpolar, water is polar, so they do not mix, right? We all have experience with oil and water mixing, and you can shake it up and you can break the oil into small droplets that are temporarily suspended in the water. But if you let it sit, the oil is going to separate itself out from the water and form two separate layers. In an emulsion, you add what's called an emulsifying agent, something that is able to stick to both the nonpolar and the polar components of your mixture, and therefore keep them mixed together or blended. And so that is what an emulsion is. You've got oil droplets in water, and usually you use an egg yolk, which, like I said, is called the emulsifying agent because it keeps the oil droplets dispersed in the water. So here's an example of an emulsifying agent. So we've got here, this is our emulsifying agent. Okay, we got, this is, what do you call it? Italian dressing. So you've got the nonpolar branches here that are going to dissolve in the oil, which is here. And then on the other side here, we've got acetic acid or vinegar. That's what acetic acid is. And you've got the polar branch, the polar half of your emulsifying agent that is going to stick to the acetic acid and the water. So you've got your oil droplets on the right-hand side that stick to the nonpolar end, and your acetic acid and your water stick to the polar end. And then that's what keeps it distributed evenly in the salad dressing bottle or in your mayonnaise. So these are different classes of colloids here along the left-hand side. There are the phases in the middle and examples. So a sol is a solid that is dispersed in a liquid. An example are paints and mud. You've got gels, which is a solid network extending through the liquid, and gelatin is an example of that. Liquid emulsion, a liquid dispersed in liquid, milk and mayonnaise. Now, milk is a mixture, again, of water and fat or cream. The fat comes in the form of cream. So in the olden days, when they didn't used to what's called homogenize, and if you understand the word homogeneous mixture, you can kind of infer what homogenize means. But now what we do is when we get the milk from cows, because I used to work in a milk factory, like testing and making sure that all of the components were correct. So we get in a big tanker truck full of raw milk straight from the farm. We test it for antibiotics and make sure that none of the cows that are giving milk are sick or are on any kind of hormone therapy or anything like that. And then once it's approved, then it gets pumped up to the homogenizing room. And then that's when you basically, I don't even remember how it works anymore because it was so long ago that I worked there, but you basically make it so that the fat from the cream stays dispersed through the watery part of the milk. And that's what allows us to buy milk in bottles that stays good for a couple weeks or a month, however long the shelf life is, without the cream actually settling out. But in the old days, I don't know, maybe ask your grandparents. I think your grandparents are probably old enough now that it used to be when milk, I don't know how they did it here in Thailand, but in the States, you used to have the milkman come with glass bottles. They would bring you like a little 6-pack of glass bottles of milk, but the milk had already separated. So you'd have to actually, I think, physically mix it up again. Anyway, so that's an example of a colloid. Then you've got foams. This is gas dispersed in liquid, like shaving cream, whipped cream. This is why they're always in cans of compressed air. And so they use that gas to help disperse the liquid and make it a foam as it comes out of the nozzle. You've got solid aerosol. We see this a lot in Thailand, especially with the big trucks. Solids dispersed in gas like smoke and auto exhaust. So that black exhaust that comes out of trucks. You've got liquid aerosol, liquid dispersed in a gas. Aerosol spray, I guess like hairspray. I don't know if you guys use hairspray. You got fog, mist, clouds, but also hairspray will be the same thing. And solid emulsion, which is a liquid dispersed in a solid, as in cheese and butter. So all of these are all colloids. They're basically one substance that is evenly dispersed through another substance, but it's not dissolved. That's the big thing, not dissolved. Okay, now we have the Tyndall effect. Almost finished. All right. Colloids can appear homogeneous because the individual particles can't be seen. Like if you look at things I just talked about, cheese, butter, clouds, things like that, it looks homogeneous because you can't see the individual particles, but we can see the effect of the colloidal particles because they scatter light. So think about like a really foggy morning or a foggy evening, and you are in the car and the headlights are on and you can actually see the beam of light coming out from the car. That is the Tyndall effect. That occurs when light is scattered by colloidal particles that are dispersed in a transparent medium like the air. And this is an example of the Tyndall effect, where you can actually see the rays of light through the air, and that's because of colloidal particles that are dispersed through the air. So here is a table that distinguishes between solutions, suspensions, and colloids, and they basically go in order of particle size. So we've got solutions, which are 0.01 to 1 nanometer, colloids 1 to 1,000, and suspension over 1,000. Solutions are the only mixture that are homogeneous. Colloids and suspensions, oops, keep losing my connection here. Oof, there we go. Solutions and, whoops, no, go back, dude. Not solutions, I mean suspensions and colloids are, oh great, no, my iPad's on the wrong slide. Okay, I'll just try to guess where it is. Colloids and suspensions are both heterogeneous. Then you've got solutions do not separate on standing, which means basically you just let it sit there. Colloidal particles also, do not separate on standing, but for a suspension, the particles fall to the bottom. For filtration, solutions and colloids cannot be separated by filtration, but suspensions can. And lastly, the solutions do not scatter light because the solute particles are completely dissolved. Colloids scatter light in the Tyndall effect. And for suspension, the particles can scatter light, but the particles also are not transparent. So you would actually see the particles. So that's many different ways of distinguishing between the three types of mixtures. Okay, I think this is the last thing. When it comes to solutions, we distinguish between electrolytes and non-electrolytes. And I'm assuming that you can probably guess what this means. Substances that dissolve in water are classified according to whether or not they produce molecules or ions in solution. When an ionic compound dissolves, the cations and the anions separate and are surrounded by water molecules. This whole process is called dissociation. Dissociation. And I want to make sure that I distinguish between dissociation and ionization because they're completely separate processes. Dissociation is for ionic compounds only. And it just means, like, if you think of the word associate, like if you and I are associated, that means that we're kind of like connected, right? Or like we're, yeah, I guess we have some kind of relationship or connection. If you are disassociated, it means you are separated, right? So dissociation is just the separation of ions when something ionic dissolves. So if I have NaCl as a solid and a dissolvent in water, I get sodium ions and chloride ions. This is an example of dissociation. We are not creating the ions, and this is the distinction between dissociation and ionization, which is another topic that comes up in this unit. These ions were there before. They were just in solid form. You're not actually creating ions. However, if I take hydrogen gas and not hydrogen gas, hydrogen chloride gas, G. and I dissolve that in water, I form hydrogen ions, which of course will basically be hydronium, which I'll talk about later, but just for simplification. This is an example of ionization. This is actually creating ions where there were no ions before, because the bond that exists between hydrogen and chlorine in HCl is covalent. It's not an ionic bond. So there are no ions in HCl, but by dissolving the gas in water, you're actually creating ions where there were not ions before. That is called ionization, but there is a difference between dissociation and ionization. Either way, these two substances would be considered electrolytes because they either separate the ions that already exist or they create ions. But the important point when it comes to electrolytes is that these ions are free to move, making it possible to carry an electric current through the solution. So an electrolyte is any substance that dissolves in water to give a solution that conducts electric current. For example, sodium chloride. Sodium chloride is not an electrolyte as a solid because the ions cannot move. And the important part about an electrolyte is that it has substances that have a charge, whether it's an electron or it's an ion, but it has something that with a charge that is able to move, and that is what carries electric current. The other example that I showed you before with hydrogen chloride, that is a highly polar compound that also can become an electrolyte because it's highly polar. It's easy to create the ions because of the polarity between the two elements. So in this example, and you can try this at home if you have electric wires, I guess, it's pretty easy. If you dissolve salt in water and you connect each wire to one of the ends of the battery, it can keep a light bulb or can light up a light bulb because it's an electrolyte. If you do that with pure water, it doesn't work because water doesn't really ionize to a large enough extent that it will carry a current. A solution containing a neutral solute does not conduct electric current because it doesn't have mobile charged particles. For example, sugar. If you dissolve sugar in water, sugar is a neutral molecule. Even though it dissolves, is not actually releasing or creating ions, and so it's a non-electrolyte. Okay, so here's 3 examples of solutions and whether or not they are electrolytes or not. So we have a salt solution. That is absolutely an electrolyte because the salt dissociates into the sodium ions and chloride ions. We have sugar, which is a non-electrolyte because sugar is a neutral molecule. It just dissolves, but it doesn't actually ionize or dissociate. And we have hydrochloric acid, which is the same example that I gave you before, which is hydrogen chloride gas, which dissolves in water, and you get HCl aqueous. And aqueous basically means it's dissolved ions. So it would be better represented with hydrogen ion and chloride ion. However, the hydrogen ion is extremely unstable and will immediately react with a water molecule to form hydronium up there. Either way, you still create ions. So this is an example, part A is an example of disassociation. B is just dissolution or dissolving, and C is ionization because you're actually creating ions.